All right, taking questions? Yes, what was your question? What page? 55. I'm flipping over to page 55 in my practice exam reader. That's winter 17, does that sound right? 23, the one where I'm filling in the blanks in a table. Okay, this was the Rydberg example that we had done earlier. You're looking at this one right here. So let's go back to that example that I did. Let me see if I can find it. Okay. This will be identical to this one, except we're going from 10 to 9. 10 to 9. Okay? So you're going to use this formula. You'd go 10 squared here, 9 squared there. And you calculate the energy. You'd put that energy right here. Okay? Then, after you found that number, I would solve for nu next. It doesn't matter what order you go, really. But you're going to take the answer for this one, and you divide it by h. So nu equals delta E over h. Put that number right there. Then, another easy one to go for is the wavelength. You're going to have to convert to nanometers, but it's hc over delta E. Just rewriting this formula down here at the bottom of the screen. This will give you, anybody, what units for lambda? Meters. So you want to convert that to nanometers before putting that number in here. So you got those three right there. Okay, once you have those three, you can get this. Notice the wavelength in meters here. So you're going to take this answer, look on this scale, and figure out what it is. So for example, we have the answer here. That's number 23. Shoot, which one was the wavelength? The first one. I think it's 38,860 nanometers. Did I read that right? Let me make sure. 38,860 nanometers. Okay, this is in meters, so I have to convert back. Oh shoot, I didn't think I was going to do math today. Okay, let me get my calculator. Just want to make sure everybody can read the table. Clear? There we go. 38,860. And then I have this E button. Most of you might say double E. E. Nanometers. If I want to go to meters, would I go -9 or +9? -9. So my minus sign is here. Minus, hopefully you can still see that. -9. Okay, 3.88 times 10 to the -5. There's the -5 right there. Anybody, am I to the right of that or to the left of that? Of this -5. If it's 3.88 times 10 to the... Yeah, slightly to the left. It's slightly larger than that number. Wouldn't matter though, infrared is still the answer. Okay, to get the last one, the de Broglie velocity, that one's not from what I've written down so far. It's on the back. Lambda equals h over mu. H is Planck's constant, that's given here. Lambda is, we just solved for it, that's that 38,000 number. The velocity is what you're asked for. And then the mass, I believe this is an electron, and the mass of the electron is given on the back of the exam. Is that okay? So that would be, this is all plug and chug. You just got to find the right formula. Sound okay? Cool. Who's next? Yes? 2017? Okay, let me find that. I'm looking for number 8, you said? Okay, yeah. So in this reaction, aluminum, that one, blah, blah, blah. Okay, this is number 8, it's at page 52, right here. little bit. Okay. Here, STP, okay. Is collected for every mole. Okay, it looks like we got to do a little bit of calculation. Let's see. Maybe we could do one of those, and hopefully I'll set up a nice pattern for you. Figure out the rest. Just got to figure out for which one does this work. Okay. So, for example, 67.2, I'm just looking at A here. We'll see if this checks out. Liters of H2 at STP, and I mean this. It's an older exam, so it's using atmospheres still. Is collected for every mole of aluminum reacted. So what I'm going to do, this is stoichiometry using the law of combining volumes. So what I'll do here, it's 1 atmosphere, so I'm going to do 22.4 liters per mole. That gives me moles of H2. Now let's double check. This looks balanced. I'm going to trust those numbers for a moment. And I'm going to say, I want to go to aluminum, so 2 moles of aluminum for every 3 moles of H2. If I don't get 1, then A is wrong. Do you want me to do another one? Is there another letter that's super exciting for you?
Well, I put B and the correct answer was C. I just want to know why C is correct.
You'd have to do the calculation, so why is C correct? So let's look at C. 1.24 centimeters cubed. So I really want to convert to liters, so I could use this. So I believe 1 centimeter cubed is 1 milliliter. 1,000 milliliters is a liter. And then 22 point, same idea here, liters per mole. And let's see where we're going this time. We're again going to aluminum, but we're going a little further. This one's a little more annoying. 2 moles of aluminum for every 3 moles of H2, but I'm not done yet. I have to get to milligrams. Oh gosh, I need to zoom out. So what is it, 26.98 for aluminum? Yeah, 26.98. This is grams per mole. And then I need to go grams per 1,000 milligrams. Sorry, I squeezed it in there, but hopefully that kind of made sense. So if I get a 1, I'm happy. Yeah, so that's basically what you look for. It's just different variants on stoichiometry. If I was going through this just strategically, I'm not seeing any that really pops out at me, so I might just like start at A and just make my way down. Or just go randomly and see if you get lucky. Okay, I would, if it was my first take through, if I get the right answer, I would move on and then come back to double check my answer if I have time. Okay, a couple people, 1 and 2 and 3. Yes? 2013, I think I heard you say. Winter 13. Wow, I didn't have that so far back. Okay, here we go. What number? 15. Looks like we got a multiple choice. I can see why you're confused because we didn't cover that yet this quarter. This one right here. So that'll be on the final, but not on our exam too, because we haven't got to radius yet. Don't worry, we'll get there. Okay, it depends on the exam, when the holidays are, what quarter. This is winter, so I'm usually able during winter quarters to get to radius for exam 2. And because we start on a Tuesday. Whatever, irrelevant. Who was 2? Yes, well, you'll be number 4, because I think I got to pick it up here. Yes. Winter 17, back to 17. Okay, that's the nemesis for a lot of y'all. Winter 17. You said number 2? Oh yeah, average 59.1. Looks like a tough one. Are we looking at this one? I don't think, I think I put reducing agents. Of course, I'd be happy to do this one also, but I believe reducing agents was on exam 1. So I'm not explicitly, I don't know where you went now. Oh yes, it's gonna ask you about reducing agents. So you wanna save this one for the final. ask me there. There's somebody over here? Yes. I'm going to page 62 right now. This looks like fall 15. What number? 11. Oh, okay. This is similar to the one I did at the beginning, the spin-up electrons. Okay, similar to the one I did at the beginning, but I'm more specific here. No. Did I read? Oh, 11. On the following set. Okay, so I'm more specific here. I give you N and M sub L. With the one I did at the beginning, I just give you N. So it just fine-tunes it a little bit. So that's page 62, fall 15, number 11. It says N is 4, M sub L is 0. Okay, so I want to know how many spin up electrons do I have? Oh, was it spin up? Doesn't really matter, but spin up. Okay, so let's just go through. If N is 4, what could L be? So what's the lowest number L could be? 0. What's the highest it could be? 2, 3. Okay, now let's double check. Do all 4 of those values give this M sub L value? Yeah, 0 does, 1 does, 2 does, and 3. So independently, all 4 of those values would give this M sub L value. Now, a 3 would also give 3, 2, 1, and negative 1, 2, 3. I don't care about those because it told me I have to stick with this one. Okay? So, here, this one would give a 0, that one would give a 0, this one would give a 0, and this one would independently. Now, they would give more than that, but again, I'm restricted with the M sub L value equals to 0. Okay, how many total orbitals do I have? Good. Oh, great question here. Not 16. Less than that. 4. How do you get 4? You count up the M sub L values. 1, 2, 3, 4. So remember, the number of M sub L values is the total number of orbitals. 4 M sub L values? 4. So, how many total electrons could I have? I didn't ask me for total electrons, but I have 4 times 2, or 8. But there would be 4 of the 8 would be spin up, so that's the answer here, and 4 of the 8 would be spin down. Is that kind of okay? Okay. 3, there was a 4 up here somewhere? Yes.
Number 13, fall 2017.
Okay, just a second. I'm going to fall 17, I think. Number 13, that's a multiple trace also. This is page 49, fall 17. Right here. Determine the initial orbit from the spectral is the final orbit. So it's just a variant on Rydberg. The way I know it's Rydberg is they give me an N value. So that's really the only equation that N is given. So there's no, usually you have both N values and you're going to energy or wavelength or frequency. Here they give you wavelength and you go into the N values. It's the same idea though, plug and chug. So let's just set up the equation to make sure you got it. Here. Delta E, which equals hc over lambda, equals the Rydberg constant, 1 over n initial squared minus 1 over n final squared. Let's make sure we know what all the variables are so you feel comfortable with it. H, constant, check. Hopefully that's okay. C, constant, check. Lambda, given 656, but what's the problem with that number, anybody? Yeah, it's in nanometers, you gotta change to meters, so make sure you do that. Rydberg constant, check. And then I know one of the n's, the final orbits, that number right there is 2. So the only variable is that one, n initial. So plug and chug. Is that cool? Okay. Cool. Who's next? Yes? Winter 17. Whoa. Oh, same place. Number 16? Or I guess 53. I somehow ended here. Okay. Here, you want to look for the key words here. The key words are accuracy, uncertainty. It's an uncertainty principle. There's really, before I even look at the numbers, it has to be. Now let's just double check the numbers. There's the position. We've got an electron, so I know it's mass. There's the percentage, which is typically given at mass about the velocity. So let's just kind of set it up and see if we got it. Okay, so here's the uncertainty principle. X, mass, to U. You can change this to an equal sign. Usually makes students' lives way easier. H over, shoot, I think it's 4 pi, isn't it? 4 pi. There we go. There's the H. Okay, I'll put a dot since I wrote this too tiny. I know H, that's a constant. 4 and pi are in your calculator. Okay, let's see what's asked for. Uncertainty in determining the velocity. So I want that one. Mass is the mass of the electron. That's given on the back of the exam. Make sure that's in kilograms. So all these should be SI units. The position, make sure it's this number right there, but that better be in meters. So change from nanometers to meters before plugging in. And then there's one more number you got to stick in there. I'll do that in blue. You got to multiply 0.01 into the top because you know it within 1% of the radius. Okay? Now, this will all give you delta U, which is the uncertainty of knowing the velocity. It's not the velocity itself. It should be a relatively large number. The reason is, so conceptually, if you have something small like an electron, the uncertainty is high of knowing it. So if you wanted to save time, and I just wasted the environment right here, it has to be A, because that's the only big number. Small, small, small. A is the correct answer for sure. So you don't even have to do the math here. And I did that on purpose so folks who knew the concept could have just boom, done, and move on. Now I would have just circled A, moved on at the end of the test and gone back and done the calculation to see if I really get that number. That's how I would have done it, to maximize time. Okay, who's next? Got a couple more minutes. Okay, there's 2 of you in the back. 1, 2, 3. Well, maybe 4. We'll see. I will have 8 minutes. Okay, one of you is 1, whoever wants to be 1. Okay.
Page 48, number 1.
48. Number 1, this is fall 17. Oh yeah, to simplify the unit thing. Classic question. You'll see it fairly often, I guess I would say. I just want to know that you can know what units mean. So let's see, second squared. So you want to know what a Pascal is. You better know what a Newton is and a joule. So get those stuck in your brain because we don't give those to you. Okay, so you see Pascal here. A Pascal is a Newton per meter squared. Think of pressure is a force per unit area times a meter over a kilogram. You can see that one of the meters are going to be gone from there. Okay, a Newton now. A Newton, so we got a second squared. We got a Newton, which is a kilogram meter per second squared. Or you can think of force is a mass times an acceleration per meter over a kilogram. And now you can see everything's going to be gone. Kilograms gone, second squareds are gone, and the meters are gone. So unitless. Okay? Good. So get used to these 3 units if you don't know those composite units. Okay, 2.
Fall 13.
Fall 13.
Number 1.
Fall 13. That quarter is page 77. Number 1, also unit question, same idea. So here, we're going maybe to the composite. We'll see. So number 1, a meter per second times a kilogram times a meter. Okay, so here we're kind of going backward. Let's see. This is a kilogram, meter per second times. There's a couple ways you can do this. If you're uncomfortable going to the composite, you can work backwards on all of them. Maybe that'll be easier. So let's do that just in case. I was going to go the other way, but I thought that might be too crazy. So Newton is a kilogram meter per second squared. Nope. A joule is a Newton meter. Think of an energy as a force times a distance, and that's times a second. Let's simplify that. A Newton is a kilogram meter per second squared times a meter times a second. So that will give the meter squared, and one of the seconds we can't, oh, it looks like it's that one. Do you see how that works? So I was about to go this way with it, but that's a little crazy. So we just went backwards. So if you're not sure, if it's one of those that's going to the composite, then you can just go through each answer and simplify each answer. Yes, on this?
Yeah.
Go
Is
ahead.
that going to be given to us, like what a Newton is?
Nope. No, not in my class. I doubt in other classes either. Again, where was that? Know these 3. What's a Newton? What's a Pascal? What's a joule? That's all on you. Okay, 2, 3. Somebody down here? Yes.
Could you do
Winter 17. Winter 17, that's page 52. Number 6. Number 5, we take that back. Number 5. Let's see, can you see this? As the temperature of a gas in a sealed rigid container is increased, so the temperature goes up, but sealed rigid container means the volume doesn't change. Rigid container means the volume doesn't change. Sealed means the moles don't escape, so the moles don't change. What happens to the density of the gas? There's a couple ways you could have done this. You could have done density is mass over volume. It's one of the variants of the ideal gas law. So you would say, okay, volume's not changing. If nothing's escaping, the mass is not changing. So it sounds like the density does not change, C. You could have put the ideal gas law all together. So you go PV equals nRT. And the other equation in the variant of the ideal gas law is the molar mass is the mass over the moles. If you stuck these all together, and kind of derived a composite formula with the density equals blah, 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 something, you get to the same answer. Because the volume and stuff like that aren't changing, the density stays the same. So you could have done it either way. Okay. So that was the variant of the ideal gas, but no calculation. So concept related. Okay, 3, 4. There was a 4 somewhere. Yes?
Winter 17, number 13.
Winter 17. Wow, we're going fast, making good time. It depends how hard this one is, though. Okay. Oh, yeah, this is doable. So, this is a good example of Graham's law, actually, I think. So you see some keyword. When I see a fuse and time, those are some key units for Graham's law. Also, I see 2 things here. So I see kind of a mixture where there's 238 and 235. So that's what's making me think Graham's law. I've got the mixture idea, and I've got some of the key units in play. Okay. Let's see. That many moles of this will fuse through a hole in 125 seconds. How many moles of this will fuse through the same hole in the same amount of time? Okay, I'm going to circle 2 numbers. The one on the left and the one on the right. One of those numbers we're not using, left or right. Which one will we not use?
Right.
The one on the right, how did you know that? That's correct. That's that extra number that doesn't mean anything. It says same amount of time. So it's just keeping the experiment integrous by saying we did the measurement holding other variables constant. That's all it's saying. So the 125 you don't need. You want to know how many moles. So this is an amount per amount. So if I could just set it up, there you are over there. If I could just set it up for you and you could solve, what you want to do is go the amount and then pick either one you want. Usually the one that's asked for I put on the top, but that's irrelevant. So the amount of the uranium-235 over, what was that number? 4.8 times 10 to the minus 5. That amount equals the square root of the molar mass of the 238 divided by the molar mass of the 235. Is that okay? So there's only going to be one unknown, which is the amount. Okay. Anybody else left over? No? Cool. Awesome. Oh, there, sorry. All right. Wow, we're ending right on time. Okay, cool. I hope you have a great rest of your weekend if possible. We'll post this in a couple days, given it recorded. Otherwise, have a great night.